Hello everyone, welcome back to the course on measurement and instrumentation, and today we are going to start our 7th week of discussion, and this is the third module that we are going to start today. And as promised earlier, in the third module we will be talking about the transducers, okay, and this is the first lecture of the 7th week, okay. So today we will have a general introduction of transducer, okay, but sometime it is very confusing that what is a sensor and what is a transducer. We will just try to define them at least in the perspective of this particular course. The definition, they may vary depending on the textbook and reference book that you are referring to. Okay. However, in this course we will be focusing on the definitions that we are going to discuss in today's lecture. Okay. So let's define a transducer first, and then we'll talk about the sensor. But this course is mostly based on the transducer, particularly this particular module. Okay. So we will mostly focus our discussion around the transducer. Alright. So a transducer is a converter of any one type of energy to some other form of energy. Okay. So what I mean to say that a transducer, say I am representing it as a black box. Okay. So if I have a transducer, okay, it can convert, say, a form of energy, it is say heat energy, alright, to say another form, say chemical energy, alright, or say other way around. So I have a transducer, so this is a transducer A, this is transducer B, okay. It can convert, say, chemical energy to, say, heat energy, alright. So this is a way how the transducer actually works. Whereas the sensor, particularly the electrical sensor that we are going to discuss, maybe in brief, but we will focus mostly on the transducer, okay, convert any type of energy into mostly electrical energy. So if I have a sensor A, okay, or say sensor B, okay, they will convert, say, form of heat energy to electrical energy, okay, then say from chemical energy to, say, electrical energy, and so on. Alright. So a transducer in a nutshell is a converter of any one type of energy to another type of energy except the electrical energy, and the sensor converts any type of energy to electrical energy. So if you see this broader definition, okay, you can say that the sensors are mostly subset of a transducer. Alright. So if we see the key characteristic of a transducer, they perform energy transformation. So one form of energy to another that we have just seen. Okay. The output can be non-electrical, but as I have told, the exception case is the sensor, which is also kind of the transducer that we are discussing. So output can be non-electrical in nature. Okay. And they are used in both measurement system and in energy conversion system. In our course, we will mostly see them as a part of measurement system, okay, and they can function as input device as well as the output device, okay. So when I say output device, means that any form of energy will be the input of the output device and the output will be in the electrical term, because we are discussing this course in a electrical course. Alright. So if I take an example, simple example of a transducer can be a loudspeaker. Okay. This loudspeaker can convert the electrical signal into a variable magnetic field and then subsequently into acoustic wave. So what you are using as an input is basically electrical energy, okay, and then you are converting it to another form of energy, say magnetic energy, and then you are converting that to, say, sound energy, or you are converting that to acoustic waves that we usually hear. So one of the good example of the transducer can be loudspeaker. Okay. Similarly, you can take other examples to understand the transducer in detail. Alright. Now there is one more term that may come in this course, that is a actuator. Okay. So two terms we have already distinguished, the sensor and the transducer, and another term that comes is the actuator. Okay. So transducers may be used as a actuator in various systems. An actuator can be described basically as just opposite of a sensor. Means that if you remember the definition of sensor, what we have done is we have given a non-electrical energy to the sensor and the output was a electrical energy, while the actuator can be described in the just opposite way of the sensor, means that it converts the electrical signal into a non-electrical energy. Okay. So you have a sensor, you have given an input as certain in a non-electrical form. So this is useful energy, any interesting non-useful energy, but in non-electrical form. All right. So it is non-electrical in nature. Okay, and the sensor will convert this into electrical data. All right. Now actuator, you are pushing some electrical signal or pushing some electrical energy, and the actuator is mostly a moving part. Okay, and it is converting that into certain useful energy, maybe in the form of motion or something else. All right. A good example of a actuator. Okay, so this is sensor vs transducer vs actuator. Okay. An electrical motor can be considered a good example of an actuator because it converts electrical energy into a mechanical action. You provide electrical energy to the motor and it starts rotating. All right. Another example is a pneumatic actuator that is enabled by a electrical sensor. An actuator transforms electrical commands into useful physical effect, and the useful physical effect is not limited only to this kind of motion. Okay, it can be related to other physical effects like force, it can be related to pressure, heat, flow, sound, etc. All right, but this is a generic definition of a actuator. Okay. So if I have to define a sensor, that we have already done in very brief. Okay, in the broader sense, the complex sensors can incorporate multiple transducers that we have just seen as an example of, say, input transducer and output transducer. That the transducers, or if you talk about the sensor in general, okay, the complex sensors may have multiple transducers. Like consider a case that, say, I want a chemical energy, okay, getting converted to electrical energy. Okay, because I am looking for a sensor which can convert any chemical energy to electrical energy. However, I am not having such sensor. Okay, what we can do is we can have multiple transducers, okay, which can convert this chemical energy to another energy, say X. Okay, now I have, so this is done by, say, a transducer 1. Okay, this is done by a transducer 1. Okay, and I have another transducer, transducer 2. Okay, I have another transducer, transducer 2, which can convert this X to Y. Okay, now this Y is, say, for example, the chemical energy. Okay, now I have a transducer 1 and 2. I am putting the input as chemical energy. The output is X. So S2 that you are seeing is X. Okay, now X is being fed to transducer 2, and say S3 is certain value Y. Okay, now I have a sensor which have the ability to convert this Y input or form of energy, this may be some another form, say sound energy, okay, to the electrical value. All right. So I have converted this chemical signal to certain value X, maybe heat. Okay, now this is converted to another phenomena, and now this is converted to electrical signal, and this is a typical example of a complex sensor. Okay, so what you are just seeing right now is a complex sensor may have multiple transducer as its part. All right, so transducer can be part of the complex sensors. Okay, now let us see different ways of classifying these transducers, okay, because they play very important role in measurement of physical quantities. Okay, so there are multiple ways to classify them. Okay, like they can be classified based on the transduction form. Okay, we'll discuss them, what it means. Like I can have different form of transduction, like I can have capacitive devices, I can have resistive devices, etc. Okay, transducer can also be classified as primary and secondary transducers. Okay, there are classification of transducers as passive and active transducers. Okay, they can also be classified based on what kind of signal it is giving in the output as analog and digital transducers, and we have a unique category of classification of transducers as a simple transducer or a transducer and a inverse transducer. Okay, so let's see them one by one so that our concept of this classification of transducers is clear. Okay, so let's see first the different type of transducers based on the transduction form. All right, so this classification is done depending on the transduction principle, means that how the input variable is being converted into capacitance or to resistance or to inductance values. Okay, these are named as capacitive transducer, resistive transducer and inductive transducer because their phenomena or their base is these kind of transduction technique. Okay, so what we will do is we will try to understand them with certain examples. Okay, let's understand it with the example of a capacitive transducer. The idea is very clear that you are using the capacitive principle to detect something. Okay, like one of the example can be a dielectric gauge. Okay, so dielectric gauge is used for the measurement of thickness. If you are dealing with liquid, they are used to measure the level of liquids in certain vessels. Okay, so capacitive transducer may found application in these areas. Okay, where you are tuning or you are changing its dielectric value by certain parameters. Okay, and that's how a dielectric gauge works. Okay, so if you see simple equation of say parallel plate capacitor. Okay, so you have C is equal to epsilon, say I am considering only epsilon. Okay, A by D, where say if it is a parallel plate capacitor, D is the distance between plates, A is the area and the epsilon is the dielectric constant of the material, that is our dielectric material between these two plates. Okay, so this capacitance can change by multiple ways. If there is a change in this dielectric material, this capacitor will change. If there is certain change in the area or if there is a certain change in the distance between the two plates, okay, this capacitor value will change. And say if the change is delta C, if you are able to detect this delta C, you will be able to detect the quantity that is under measurement. For example, as I have mentioned that with the dielectric gauge you are measuring, say for example, thickness. So with the thickness change, there is a subsequent change in this capacitor in the form of this delta C, and if you are able to measure this delta C, you are able to measure the thickness of the of whatever you are measuring. Similarly, you can extend this knowledge to the liquid levels, right? Then examples of the capacitive transducer can be capacitive microphone. Okay, so it is used to measure noise, maybe speech and musics. Okay, so these are certain examples of capacitive transducers. Okay, then there are several ways to define resistive transducers, and they are very much useful for multiple applications. Okay, so resistive thermometer, for example, they are used in the measurement of temperature, measurement of radiant heat, etc. Okay, then another application of the resistive transducer is in the potentiometer devices, which are used in the displacement measurement and they are used in the pressure measurement and so on. All right, you have potentiometer devices as the position of the slider changes by external force, the resistance in the potentiometer or bridge circuit changes, and based on that you have displacement sensors, you have pressure sensors and so on. Okay, resistive strain gauge, that we will also discuss in detail. Okay, so these resistance of a wire or say semiconductor material changes by elongation or compression due to externally applied stress. Okay, and we have seen that R is equal to rho L by A. So if there is, say, this rho is the resistivity and this is the resistance, and L is the length and A is the cross sectional area. If there is any change in this L value or A value, okay, this R will change, and say if the change is, say, delta R, by measuring this delta R, the applied force, torque or displacement can be measured. Okay. Then there are other examples of resistive transducer like Pirani gauge or hot wire meters, where resistance of a heating element is varied by convection cooling of a stream of gas, and they are very important for applications such as monitoring the gas flow or monitoring the gas pressure, etc. Okay. So similarly, we have resistive thermometers, thermistors, okay, resistance hygrometers, where resistance of pure metallic wire changes when there is a change in the temperature, okay, and that's how resistive thermometers are designed. Okay. Similarly, for the thermistors, we know that it is based on change in the resistance of certain kind of semiconductors, particularly metal oxides. So we know that resistance of several metal oxides, mostly they are negative temperature coefficient, okay, changes when the temperature changes, and that's how they are used for the monitoring of the temperatures. Okay. Similarly, we have photoconductive cells. Okay. Then there are various ways of using these transduction principles, okay, to measure different quantities by measuring the change in the inductance, similar to one that we have seen for capacitance and resistance. Okay. And magnetic circuit transducer, for example, is one of the good example for the inductance or the transducer which are based on the inductance principle or change in the inductance principle. Okay. So self inductance or mutual inductance of a AC excited coil is varied by change in the magnetic circuit. Okay. And that's how you use it for any minute change in the pressure or minute change in the displacement. Okay. Similarly, you have reluctance pickup coils. Okay. So reluctance of a magnetic circuit is varied by changing the position of the iron core of the coil, and they are very much useful in measurement of small pressures, displacements, vibrations and positions of many objects. Okay. Now the transducers are also, some of the transducers are very much sensitive to change in the voltages and change in the current. Okay. Like we have devices like Hall effect pickup. Okay. So like similarly ionization chambers, photoemissive cells, photomultiplier tubes, where there is a change in the current or there is a small change in the potential drop. Okay. Say for example Hall effect pickups. Okay. In this case a potential difference is generated across a semiconductor plate. Okay. When magnetic flux interacts with the applied current, and as the name suggests, they are based on the Hall effect principle. Okay. And they are used for applications such as measurement of magnetic flux, measurement of current or measurement of power. Okay. Similarly, for ionization chamber, the electron flow induced by the ionization of gas due to radiative or radioactive radiations are measured. Okay. And they can be used for the particle counting and for the monitoring of kind of radiation it is emitting, like that. Okay. Similarly, photoemissive cell are something where electron emission due to incident radiation upon photoemissive surfaces are used to monitor the light and the radiations. Okay. So these are different examples of how transduction technique can be tuned to use this transducer to measure a certain kind of physical parameters. Okay. Now we have also defined transducers as active transducers and the passive transducers. Okay. So the transducers which does not require any external excitation to provide their output are referred to as the active transducers, and the good example of active transducer is, say, a photovoltaic cell. Okay. So we know that what is the application of photovoltaic cells. They are basically the solar cells, or they can be used in the light meters. Okay. Similarly, thermocouple is another active transducer, where it is used to measure the temperature, heat flow, radiation, etc. Alright. Now the passive transducer are those which requires an external excitation to provide their output, and then most of the transducers that we see around, be it capacitive, be it inductive, be it resistive, they are all kind of passive transducers. Alright. Then we have analog and digital transducers. So the transducers that produces their output in analog form or a form which is a continuous function of time is referred as a analog transducer. Okay, and good example can be like a strain gauge, okay, which is used to measure displacement, force or torque, and even the continuous variation of displacement can be seen as a continuous signal as an output from the strain gauge. Okay, similarly thermistor is another kind of analog transducer where it is used for the measurement of temperature or flow, and the output is in the form of continuous and not in the form of discrete signals. Okay, and the digital transducers are those where or which produces their outputs in digital form or a form of pulse, okay, and not in a form of continuous signal. Okay, and good example can be a turbine meter. Okay, and these turbine meters are basically used in flow measurement. So if you do not know what is turbine meter is, okay, let's understand it in a very brief. Okay, so say if I have a pipe, okay, and I want to measure the flow, and this is the liquid, and I have like this. Okay, I have a turbine and these are the blades of the turbine. Okay, say just I am giving this example so that we are more connected, particularly this digital transducers. Okay, now the fluid enters the pipe and strikes the turbine blades. Okay, now the turbine rotates at a speed which is say directly proportional to the flow velocity. Okay, now a magnetic pickup or Hall sensor is kept nearby which detects where each blade's passing. Say if it is rotating, okay, and say if this is the magnetic pickup that is kept nearby. Okay, now say this is, say I am numbering this blade, say 1, 2, 3, 4 and 5. Okay, now it is rotating. Okay, now this blade 1 has passed and 5 has come here. Okay, so this is now 5. Okay, now it has counted that, okay, one blade has passed. Okay, now when this 5 is moved here, okay, now this is replaced by the blade 4. All right, so a pickup or a Hall effect sensor is used to detect each blade's passing, and now in this movement if you see, you are actually generating a pulse. So each blade is generating a pulse. So you have, say if I want to write say output of this Hall voltage or say magnetic pickup coil, okay, and say output is in some form of say voltage of the pickup. Okay, and now say output will be something like this, right, in the form of pulse. So each pulse suggests counting of passing of every blade. All right, so this if you see, the output is already discretized. Okay, so you have not done anything intentionally, but output itself is a pulsed output and the output itself is in the digital form. So this is digital example, good example of the digital transducer. All right, then we have transducers like primary transducers and secondary transducers. Okay, so the transducer which send the measurement and convert them into another variable like displacement or a strain, and whose output forms the input of another transducer is called the primary transducer, like the Bourdon tube, strain gauge. Okay, they are used for pressure and other measurements. Okay, now the secondary transducers are those which converts the output of the first transducer into an electrical output. Okay, like LVDT. Okay, so LVDT is nothing but a linear variable differential transformer, and they are used to measure a number of things like displacement, force, pressure, position, etc. Okay, then another classification that we have seen was transducer and inverse transducer. So a measuring device which measures and convert the non-electrical variable into electrical variable is called a transducer, that we have seen. Okay, example is like a thermocouple which is used to measure say number of things like radiation, temperature, heat flow, etc. Okay, now a inverse transducer is something which measures and convert electrical variable into non-electrical variable, like a piezoelectric crystal which is used to measure pressure, vibration, acceleration, etc. Okay, however, it is sometimes very confusing that what is inverse transducer and what is a actuator, because if you see actuator was also doing the same job. It was, converting a electrical variable into a non-electrical variable. If you remember, we have discussed that it is doing just opposite of what a sensor does, and exactly the inverse transducer is doing this. Okay, so it's very important to segregate between them. Okay, and this will help us in this particular course. Okay, and the definitions that we are discussing today, we will extend it in complete third module. Okay, so that we are all at the same platform. Okay, so inverse transducer and an actuator both converts electrical energy into a non-electrical physical quantity, say it's motion, force, light or sound. Okay, now sometime they are interchangeably used. So inverse transducer and actuator, they may be used their names interchangeably. However, if you see in detail, the inverse transducers typically emphasize precise low power electrical to non-electrical conversion like our analog meters. Okay, whereas the actuators are generally defined by their ability to drive high power mechanical movement, like in case of motors, solenoids and so on. Okay, however, with the rise in the different low power devices or low power device fabrication technologies like MEMS and NAMES, okay, where you can actually fabricate actuators which can deal with the very low power electrical to non-electrical convergence, these definitions are also nowadays very blurred. Okay, that's why in this course or particularly in this third module, what we will do is we will mostly use a term transducers and actuators rather than using a word inverse transducers and actuators. Okay, so we will be using the term actuators mostly for these points. Okay, there are different characteristics of these transducers, and that's how someone can choose among number of transducers, okay, based on different characteristics. Okay, and when choosing a transducer for any application, three different characteristics taken into account. Okay, the first is the input characteristic, then transfer characteristics and the output characteristics. Okay, so let us try to understand the input characteristics first before we actually go to understand the transfer and output characteristics. Okay, so for understanding the input characteristic, we have to understand the type of input and the operating range requirement of the transducers. Okay, the foremost consideration for the choice of a transducer is the input quantity that your transducer is going to measure and what will be the range of the operation. Like say I have a transducer A and transducer B. Say transducer A might be very suitable for the measurement of certain range of parameters, say 10G to 100G force measurement. Okay, so this is say transducer A. All right, it is used for measurement of this. However, I have another scenario where I need something say 100G to 1000G. Okay, and I want to measure something around say 250G. Okay, now I have a transducer which can measure the force. I have a scenario, I have another transducer basically a B which can measure the force, but our intended range of the application is say around say 120G to say 250G. Now I have a choice between two transducers which can measure the different forces, but what I will go is, if I know the specification sheet or the data sheet of the transducer, I will go with the transducer B. All right, so not only the consideration for the choice of the transducer is the input quantity, but also its operating range, which we call in module 1 as span. Right? Then loading effect is another consideration that we take into consideration while discussing these input characteristics. The transducer that is selected for a particular application should ideally extract no force, no power or no energy from the quantity which is under measurement, in order that the latter is measured accurately and no error arise because of all these loading effects. Okay, so then second characteristic is the transfer characteristics. Okay, so the transfer characteristic of a transducer require the attention of three separate elements. The first is the transfer function itself, second is the error, and third is the response of the transducer to the environment influences or the ambient influences. Okay, so let's try to understand the transfer function, because this is what actually govern the calibration and other things associated with the transducer. So transfer function can be defined as something like this. So you have this output as a function of the input, where this Qi and Q naught and Qi are the output and input of the transducer. Okay, and the ratio of these things actually gives you the transfer function. Okay, and once you have this, the differentiation or the differential quotient gives you the sensitivity of the transducer. Okay, so there is one more thing that is defined, which is the scale factor of the transducer. Scale factor is nothing but the inverse of the sensitivity of the transducer. So if you know the transfer function, okay, the slope of that basically at a certain point gives you sensitivity, and inverse of it gives you the scale factor. So scale factor is defined as the inverse of the sensitivity, and it can be given as, say, for this particular case, as 1 by dqi by dq naught. Okay, so these are some of the characteristics that we will continue discussing in our next lecture. Also, we will continue our discussion on errors and other things, particularly in the context of the transducer. Okay, so we'll meet in the second lecture of this week 7. Thank you.